This is Free Range Digital Design Foundation Modeling, Chapter 21. We're previously talking about latches, and we kind of agreed that you don't really see latches too often in digital circuits, but a similar device are flip-flops. They're also 1-bit storage elements. You see those a little bit more often, but it's actually a precursor to the next chapter, which is registers. So this chapter, everything you wanted to know about flip-flops. Okay, so a little bit of review first. And there are two types of digital circuits out there, combinatorial circuits and sequential circuits. So combinatorial circuits is what we've been working with for most of the course. Latches was our first sequential circuit, but combinatorial circuits, the outputs are a direct function of the inputs. They are said to have no state, no memory, as opposed to sequential circuits that have memory. And so the outputs in a sequential circuit are a function of not the inputs, but in particular the sequence of inputs. These circuits have memory, so thus we can refer to these circuits as sequential circuits as having state. And remember, the state is what data that particular circuit is memorizing at any particular time. We started looking at latches, which was a 1-bit storage element. The idea is we looked at this NOR latch and an AND latch. We agreed that they were roughly the same thing, except that the NAND latch was kind of a negative logic version of the NOR latch. Didn't do too much with it. We generated some tables describing their behavior, but we are going to move to a more useful circuit, which is, of course, the flip-flop. Let's do it. So flip-flops, they are also 1-bit storage elements. They come in different flavors. The three most popular flavors are D flip-flop, T flip-flop, and a JK flip-flop. D flip-flop is known as the data flip-flop for a reason you'll see in a second. T flip-flop was a toggle flip-flop. JK flip-flop was, who knows what that was? No one could ever know what JK stood for. We are not going to discuss T and JK flip-flops, and they're kind of low-level concepts. Everything we're going to do is with the D flip-flop, and which is good. It's because it's the easiest of the three flip-flops. And so the issue here is flip-flop. It's a 1-bit storage element, just like the latches were, but they have a different sensitivity. So the latches are well known to be level sensitive, which means output can change anytime the inputs change, whereas flip-flops, they're essentially edge sensitive. So these flip-flops are going to have a clock input, and the flip-flops can only change state on that clock edge. So that clock edge is necessarily very short, very tiny, very small amount of time. So in essence, latches can change anytime based on the level of the inputs. We consider that as asynchronous, whereas with flip-flops, because changes in the output are synchronized with a clock edge, we refer to those as synchronous circuits. So once again, latches, level sensitive, asynchronous; flip-flops, edge sensitive, synchronous. This is our D flip-flop here. D has a data input and it has Q output, both Q and a Q bar. So it does have complementary inputs like our cross-coupled cells, and it also has a clock edge here. And it's a very simple circuit. When this clock edge comes along, it looks like a clock edge like this. When that clock edge comes along, it takes the value on that D input here and latches it into the flip-flop, which means it puts it into the flip-flop's memory. So essentially the D can sit there forever, but the only time it really matters is when that clock edge happens. Now these clock edges, as you can see from this circuit here, you got two types of clock edges. This is a rising edge. We'll just call it rising edge triggered, and this is a falling edge. And this is falling edge triggers. This interesting little triangle here indicates that this is a rising edge triggered device. Sometimes you see these circuits with a circle there, a bubble I guess, and that would be considered a falling edge triggered device, which means changes in the output are synchronized with the falling edge rather than the rising edge. I'm going to go ahead and erase that because in this book pretty much don't work with anything other than rising edge. I actually used to do that in other other courses, other versions of this course, but it was it kind of became like a trick problem because people would forget to look at it. When you're actually doing design, you don't mess around with rising and falling clock edges. You generally choose one and stick. So the issue is there's some circuitry involved in that rising clock edge, and it's somewhat complicated, and so we just ignore that in this book. I know other digital design texts go through that quite in depth, but we're not going to go there other than to show you a picture of it, and I believe the picture is coming up. And the picture isn't coming up, it's coming up in a couple slides later. So once again, D flip-flop, it's a data flip-flop. Here's the block diagram. The way it's written is it's a rising edge trigger. A couple tables here describing the operation of the flip-flop. What we're interested in is the state change on this thing. Here's the state change. It goes from Q to Q plus is the new state. So what happens is you can see that whatever the present state is, it doesn't matter. Only thing that matters is the D, because when that clock edge comes around, this D input is transferred to the output, and you can see that the Q plus column is equal to the D column, because the Q plus column is the new state. The new state, the new data on the D input is latched into that flip-flop on that rising edge for this particular circuit. It doesn't matter what the current state is, what Q is. The only thing that matters is what D is. And you can see that this is a characteristic equation. It used to be a really important thing to work with at a low level. We don't really look at it too much anymore. What it says is the new state is equal to D. And you can see that Q plus equals the D input. This is another table here. It's described what D has to be to cause this state change. So 0 to 0, that's a D, 0 to 1, 1. So it's actually, it's just the same table, but it's rearranged differently. They call it an excitation table. Once again, we used to use that a lot. We pretty much don't use that anymore, but you can see once again D matches the Q plus column, which is what we're interested in here. So lastly, a little note here says generate a state diagram. This is very straightforward. These tables kind of describe how this works. The state diagram is going to do a better job of describing it because it gives a visual representation rather than having to chunk through the table. It's a 1-bit storage element, which means there's two states. The two states I'm going to represent with these bubbles, and I'll call it Q equals 1, Q equals 0. So there's a couple things that are going to happen in this state diagram. I can stay in that state, I can go to the other state, I can stay in that state, or I can go to the other state. And so what I want to do here is list the conditions that cause these transitions to happen. And so Q going from 0 to Q equals 0, that means D must be 0. I always like writing these as a D bar. Once you put ones and zeros in your state diagram, it starts getting hard to read. So here's a Q equals 1, this transition here, Q equals 1. The initial state is Q equals 1, and it goes to Q equals 1. What causes that to happen? D. Okay, so Q equals 1 transitions to Q equals 0. There's my D bar. Q equals 0 transitions to Q equals 1. That's D. And that is my entire diagram. Once again, these are state diagrams that are massively important. We'll spend a lot more time on that later, but the important thing to notice is that there is a clock input on this flip-flop, but there's no clock input in these tables, and there's no clock input in the state diagram. The issue is these transitions are understood to happen on the clock edge. Therefore, I'm not going to put the clock edge in these tables or in the state diagram. So this transition right here, all these transitions, they happen on the clock edge. No other way around it. That's why I really truly wouldn't even know how to represent a clock in these tables or in the diagram. We do not need a clock. All transitions are synchronized to the clock edge. That's part of the definition of a flip-flop. Yeah, so once again, we'll get into this more in depth later. Here's that promised low-level diagram of a edge-triggered flip-flop, and so this is the flip-flop that we've been looking at, and this is the underlying circuitry. So you would expect there to be a latch in there somewhere, right? And you can see the latch. But what's probably not expected in this is the notion that there's actually 3 latches in there, and when you arrange them properly, it's what gives you both the memory inside this flip-flop, and it gives you that magic edge triggering. So there's this is D flip-flop, edge triggering is not overly complicated, but it's not simple either. This is the circuitry for it. I just wouldn't want to analyze that circuit. I think I did it a long time ago. What we're interested in is how this circuit works. This is a diagram of how this circuit works. This is what I'm looking at. This is the black box diagram, associated timing diagram, and the only thing I'm interested in is these rising clock edges, which is why I put these dotted lines there. So on that rising clock edge, it is going to take whatever is on the D input and put it in the flip-flop. And so it's essentially on that rising clock edge, the flip-flop stands a good chance of changing state. So here's the first item here, Q. It starts off somewhere. I have to tell you where it starts. I have to give you initial state on it, but its initial state is 0. Here's a clock edge. On that clock edge, I see a 1 sitting in the D input, so that essentially sets the flip-flop. So a bunch of stuff goes on in between the clock edges. I get to ignore that. Here's the next clock edge. Next clock edge, it's also a 1, and so it doesn't change state. Next clock edge, I see a 0 there. That clock edge plus the signal causes it to go to reset. A bunch of stuff happens in between on the D input. We can ignore that because it's edge sensitive. Output only changes on a clock edge. Here's a clock edge at 0. Output's already at 0, so it doesn't change. And lastly here, we got a D input of 1. Flip-flop is already in state 0, so it's going to set the flip-flop. Data flip-flop. We go to great efforts to tell you that this is a synchronous device, but as it turns out, typically flip-flops can have asynchronous inputs also. So typically what you see here for flip-flops is they have a set input or a reset input. This happens to be a reset input. Once again, they can be a set or a reset input is what you typically see, and what you don't see here is it can be synchronous or asynchronous. So when you're looking at this input, typically their inputs like this are asynchronous, but you don't know. Some of them are synchronous. So when you're working with problems like this, someone has to tell you in advance whether that R input is synchronous or not. Now it's understood that the D input is always going to be synchronous, but the issue here is once you start working with something new, you got to check the data sheet, or someone has to tell you whether it's synchronous or not. So it does have the bubble there. The bubble indicates that this input is active low. Typically with these asynchronous inputs, they are active low. So here's an example here. What we have here, it's an asynchronous reset. It's not a resent, but whatever. The R is it's asynchronous and it's active low, and since it starts off low, the flip-flop is in a low state. Okay, so reset input unasserts, but the flip-flop remains low. It doesn't change state when that asynchronous input unasserts. So that's an important point. After that, pretty much what I have to do is be aware of these 3 assertions of the reset input, and other than that, it's just like a normal flip-flop problem. So the next thing I'm going to look at is this clock edge here. Clock edge, it's a rising clock edge, D's a 1, so that sets it. Here's the next rising clock edge, D's a 1, it's already set, so it really doesn't change state. And then I got this reset asserted. So once again, it resets immediately. Once the reset is unasserted, the flip-flop stays reset. Clock edge, it's a 0, doesn't change state. Bunch of stuff happening in between the clock edges. Doesn't matter, all I care about is clock edges. Clock edge is a 0, doesn't change state. And here, next clock edge, it's a 1, which causes it to change state on that clock edge. Very soon after that, I have that reset asserting again, which causes the flip-flop to reset. The reset unasserts, the output or the flip-flop output doesn't change, or you could say the data that was latched in there remains latched in there. These are important terms we've come up with up till now. These are digital circuits, 2 types, got combinatorial and sequential. Combinatorial have no memory, sequential have memory. So we've been looking at 2 types of 1-bit storage element. Initially we looked at latches. We consider those to be level sensitive and asynchronous, as opposed to flip-flops, which are edge sensitive, and the edge they're sensitive to is generally a clock edge, so all the changes are synchronized to the clock edge, so we consider those a synchronous circuit. So we've seen this before. It's the notion of latching something. A latch is a 1-bit storage element, but I can latch data into a latch, or I can latch data into a flip-flop. So essentially I'm latching data into a memory element. Common, super common term, we'll use that pretty much forever in this course. So this is a classic example using a D flip-flop. I'm going to use a D flip-flop to blink a light at half the frequency of the clock. It's a classic problem. It's one of those problems it's hard to imagine, but once someone shows it to you, you're going to think, oh, that's not too bad. So I'm just pretty much going to show this to you. We know it has a D flip-flop in there, and there's a Q output on this thing, there's a D input, and there's a clock. The issue is how am I going to set this up such that it cuts the input frequency in half. So if I just connect this, and I'm going to call this the LED output, if I just connect this like this, what I get is the output, whatever that output is, it just keeps latching itself back in there. So which is not going to work, because if I do it like that, it's not going to oscillate. But what I'm going to do here is drop an inverter in there. Okay, so let's do that. So that's the input clock frequency. The LED clock frequency is going to be, well, let's do this. Well, the LED is either on or off because it's based on the state of this thing. So when the LED is on, we'll say the LED is on. That means that on signal gets inverted and gets latched into this thing at the next clock edge, which turns the flip-flop off, which turns the LED off. So once again, the LED starts as a 1. This 1 gets turned into a 0. I have a 0 sitting there. The 0 gets latched into this circuit right there, turns the flip-flop off. So the next clock edge, I've got a 0 on the Q output. 0 becomes a 1. 1 gets turned, put into the D input, and it gets latched like that. So once again, what we see here is a waveform that looks like that. So this is the input clock frequency, and this is the output LED frequency. And if you look at this, you can definitely tell that the clock frequency is twice that of the LED frequency, or the LED frequency is half that of the clock frequency. This here is a super classic circuit in digital design. It uses a D flip-flop to cut the clock frequency in half. Remember this, it comes up a lot. Certainly it's a good test interview question. The issue is that people expect you to know that, and it's a simple idea. Sometimes it's hard to derive, but if you kind of have an idea where you're going with it, it works. This is a similar problem. We'll do it properly this time. This is a circuit. It has 2 LED outputs. We'll call it LED A and LED B for lack of better anything to put it. And what I have here is a clock coming into this circuit. So this is very similar to the last problem. It's going to blink these LEDs at half the frequency, and what I'm going to have in this thing is the frequency. Only one LED at a time is going to be on, but there's always going to be one LED on. So what that's going to look like is, in this circuit here, we have a D flip-flop. We're going to kind of copy the last design, because I know that cuts the frequency in half. And what I need on this output is, we'll just call this LED A. It looks good. What I need is also something that when this LED's on, the other LED's off, and vice versa. And essentially what that is going to be well, I thought I could just drop an inverter here, but I might as well just grab this input, put that out there. And doing that essentially saves a inverter, and life is good. Like I said, I was going to drop an inverter right here, but we don't need that. Okay, so roughly this is the same problem over again, but it's an important problem.